So the problem is if you look at the most recent state of the climate published by BAMS, which is Bulletin of the American Meteorological Society, and they have a section on ozone. And in that section, there's a couple graphs that show that the ozone hole has come back with a vengeance, as you mentioned, in 2021, 22, and 23.
Hello, and welcome to another edition of the Climate Emergency Forum. I'm your host, Charles, and today we're diving into a complex and often misunderstood topic, the relationship between climate change and the ozone layer. Our title today is Global Warming Effects on the Ozone Layer. Many of us remember the ozone crisis of the 1980s and the subsequent success of the Montreal Protocol in addressing ozone-depleting substances. However, recent data from the World Meteorological Organization shows that the ozone hole has reached record levels in 2021, 2022, and 2023. This unexpected development brings us to a crucial question. How is our changing climate affecting the ozone layer, and what does this mean for our planet? We'll explore the latest scientific findings on stratospheric cooling, its impacts on ozone depletion, and the strengthening of polar vortices around Antarctica. We'll also examine how these changes in the ozone layer might in turn influence our climate system. Join us as we unravel this intricate relationship and discuss its implications for our ongoing climate crisis. Paul, can you fill us in on your research for this topic?
Thank you, Charles. So the ozone is often touted. Correcting the ozone hole or reducing the ozone hole with the idea of eliminating it, eliminating that problem, is often used as an example of global cooperation with many different nations under, organization of the UN to result in the Montreal Protocol. So there was a summit in Montreal in 1987, and they agreed to reduce the use of CFCs, specifically chlorofluorocarbons, in refrigeration systems, because that gas was leaking up into the atmosphere, where one chlorine molecule would act as a catalyst to destroy literally hundreds to thousands of ozone molecules, and it just would stay up in the atmosphere. These CFC is one example of a halocarbon. There's other things, HCFCs and other things, and they're very long-lived chemicals in the atmosphere. So this treaty, the Montreal Protocol, was ratified 2 years later after the meeting. So meeting 1987, ratified in 1989. It's funny because the other day I couldn't remember whether it was 87 or 89, and it's both dates, both years were important. So, we thought that this was a problem that we'd solved. Now, over the years, it hasn't completely gone away. There's been a lot of variability with the size of the ozone hole. It forms over Antarctica because the air is very, very cold over Antarctica. Even in the upper stratosphere, it's extremely cold, and cold temperatures make the reaction go stronger, which is opposite to how chemical reactions normally occur. But this is a very specific one, destruction of ozone by the chlorine. So the problem is if you look at the most recent state of the climate published by BAMS, which is Bulletin of the American Meteorological Society, they published a 500-page extensive detailed document on the state of the climate in 2023. And they have a section on ozone, and in that section, there's a couple graphs that show that the ozone hole has come back with a vengeance, as you mentioned in 2021, 22, and 23. By a vengeance, I mean that it started earlier than ever. It ends earlier than ever. Its duration is as long as it's ever been since, the protocol was first put in place. Plus, the depth of the ozone destruction is huge. It sets records in all of these things, and it's not making noise globally. It's just, it's just in this lengthy report, but I've seen very little press on it, and it's significant. Because why is the ozone so important? Just to remind people, and Peter can maybe go into sort of some of the medical effects, but basically the ozone blocks the ultraviolet, and ultraviolet is a very short wavelength, and the photons, the energy packets of ultraviolet, are very powerful, and they can cut chemical bonds and cause mutations and things. So when it does this in your skin, you can get skin cancer. When it does this to your eyes, you can get cataracts. There's very serious medical issues of being exposed to too much ozone. So we need that ozone layer. And also, it's almost exclusively an Antarctica thing. So there's not many people living under the ozone hole on the Antarctic ice shelf. But we have seen ozone holes appear in the Arctic. Very rarely, but it has happened. Again, those would be exceptionally cold years. So how is climate change affecting this? Well, I can go into more detail when I talk again, but in a nutshell, climate change is, of course, warming the lower atmosphere very rapidly. Global warming. It's the lower atmosphere, the troposphere, where all the weather is occurring, that's warming greatly. Now, because it's warming greatly, greenhouse gases are up. There's more reflected heat being trapped by the greenhouse gases. So there's less heat passing through the stratosphere to warm the stratosphere. So the stratosphere is getting colder. That's an indication of climate change happening, stratosphere cooling. So as the lower atmosphere is warming, is the part we live in, where the upper atmosphere is cooling. Therefore, it's making the probability of ozone destruction higher. The other thing is over Antarctica, we've had a change in the wind patterns. We've had something called the stratospheric polar vortex. You've probably heard the term polar vortex, which is very strong winds in the stratosphere causing very cool areas, which also go against the ozone. So there's enough of the chlorofluorocarbons and HFCs and all these halocarbons still in the upper atmosphere. Some of them have lifetimes of like thousands, 10,000s of years. There's still enough there that with the cooler temperatures in the stratosphere from climate change, we're getting this ozone destruction occurring again. There's been studies that estimate the number of incidences of skin cancer avoided by the Montreal Protocol, and the fewer number of cataracts people have been subjected to because of the Montreal Protocol stuff. So now we're going to see strong upticks in these medical conditions once again, depending on how large the ozone hole is. So although it's centered over Antarctica, it still reaches towards South America when it's at maximum extent. So it does have human health effects on people, which, Peter being a retired medical doctor, I'm sure you can talk about skin cancers and cataracts and things like that in more detail than I can.
Thank you so much, Paul, and thank you for the wonderful insights you provided, especially explaining why the stratosphere is getting cooler. It makes perfect sense. And so now, Peter, I'd like to ask you to share your insights on this issue.
Well, thanks, Charles, and thank you for explaining that, Paul. So my insights on this problem are not very great at all. I get the impression that, well, when I look at the research, and I think maybe over the past 10 years or so, the interactions between, and this was anticipated years ago, the interaction between stratospheric ozone depletion, the ozone thinning, so-called ozone hole, and global warming and climate change are very many. It works both ways, and it works both ways, several ways. So in other words, the ozone depletion can, in some situations that Paul's already explained, aggravate, increase a tendency towards global warming and climate change, but it also works the other way, that climate change can affect ozone depletion. Looking back on the beginning of this, of course, the Montreal was a great success because everybody very quickly became aware that the blocking of ultraviolet light coming from space was one of the essential factors in maintaining life on the planet of all kinds. So there was a really big rush and urgency to fix that, which I got to say has not been repeated and evident for the global climate change situation. As Paul has said, we've had a few very strange years that the ozone depletion is not following the path that it was anticipated. The experts are still confident that it will eventually close. They're talking about decades away now. The Montreal Protocol was not the huge, complete success that is talked about. Dow Chemical were making the CFCs, the very potent ozone depleters. They played hardball in the Montreal Protocol negotiations, and they would only cooperate if they were permitted to make an alternative to CFCs. So we're talking about synthetic gases here. We're talking about human-made gases. The IPCC calls them F gases, the halocarbons. There are dozens and dozens of them. Industry is still manufacturing new ones. So I think we're in an extremely unsatisfactory situation with regards to ozone depletion, especially when you look at all the other gross, massive disturbances.
Okay, well, thank you, Peter, for sharing your insights regarding the health aspects of ozone and also the history on the Montreal Protocol and how it played out. That was very interesting. And also about Dow Chemical. So, Paul, can you share with us some more insights on this topic?
Yeah, so the ozone hole issue, of course, was a very different issue from climate change. You know, of course, climate change is due to the greenhouse gases, and there's multiple emitters, multiple sources around the planet, and also the ability of the sinks to absorb the greenhouse gases that we put up in the atmosphere is also a very important part of the equation. It's like your bathtub. Both the tap and the drain are both important. The tap being the sources, the emissions, and the drain being the sinks. As Peter mentioned, he mentioned Dow Chemical. I mean, there was Dow and DuPont, basically a couple companies that were involved in producing these CFCs, and the thermal capacities of the CFCs were excellent. So it was used as a working fluid in refrigeration systems around the world. But there's always leaks, and it was discovered very quickly by scientists after the product was introduced what it would do once it got into the atmosphere. Papers were published. It took a few years to get the eye of the global community, and then it resulted in that meeting in Montreal in '87. There is a bit of serendipity involved here because when the CFCs were being developed, they also looked at instead of chlorofluorocarbons, they looked at bromofluorocarbons, so using bromine instead of chlorine. And they ended up going with chlorine in the CFCs because chlorine was cheaper than bromine. But that was an incredible fluke of luck, actually, because if they had used bromine, which actually had some slightly better properties as a refrigerant coolant, then the ozone layer would have been completely wiped out before anybody could blink. Because the ability of bromine to break down ozone exceeds that of chlorine by at least an order of magnitude. Some people even argue 2 orders of magnitude. So the world basically dodged a bullet by this one company using the CFCs instead of using bromine instead of chlorine. Most people aren't aware of that, but I think it's very important for, in general, how things can really spiral out of control quickly if we don't know what we're doing. So the ozone hole, a lot of people have written off, like I say, environmentalists around the world. I bet if you talk to 10 of them, 9.9 of them would have no idea that the ozone hole has been setting records in the last 3 years, right? They assume that it's a solved problem, it's slowly heading out. But climate change is, once again, bearing vengeance on humanity and causing this problem, the ozone hole problem, to resurface. So it's not like we're putting, more CFCs or halocarbons into the air. And what's in there is they've got long lifetime, combined with the lower temperatures in the stratosphere that are directly caused by climate change, has caused this problem to not be gone. It's caused this problem to resurface. And hopefully, videos like ours, which can, I think if you had to ask what the main goal of Climate Emergency Forum is we're concerned about climate change, as everybody should be, but we're trying to educate people as much as possible, because there's lots of gaps in public knowledge. And this is something that, like I said, it was in the publication State of the Climate 2023 by BAMS, but that's a huge document. This was 2 or 3 pages. I hope that you showed links to the particular graphs that we've been referring to of 2021, 2022, 2023, because the graph shows an envelope of the ozone hole when it's over time. It's over a year time scale on the x-axis, and it's on the y-axis. It's the strength of the hole, so you can get the initiation date earlier than anything else, and the day the ozone hole basically ends. The ozone recovers, which is usually in mid-December. Duration, right, the time period when it's occurring, and the depth, in so-called Dobson units. It's the amount of UV that the ozone can absorb. And there's a gray envelope showing each year. It doesn't show the graph of each year. It shows the envelope of the highest and lowest years. There's been variability, that's in gray. And then you can see those 3 most recent years of data sticking out like a sore thumb. So, hopefully people can go and check the links that you put in the description, and they can see this for themselves and spread this information far and wide, because people need to know about it.
Thank you so much, Paul, for sharing your knowledge about this topic and learning about it from the BAMS report. So definitely is something I'm going to look at. And I'm kind of wondering, Paul, if you can share any insight on the relationship of this increase in the ozone hole to polar stratospheric clouds.
Yes, so it might be worth at some point doing a whole video on the stratosphere, because there's a lot of things are happening in the stratosphere. Probably most known is the ozone and its role in absorbing ultraviolet, but there's a lot of we're getting more water vapor in the stratosphere. Okay, so we're experiencing more extreme weather events on where we live on the surface of the Earth. And these extreme weather events can often lead to very, very intense storms, widespread storms, which can spin off tornadoes, which can create derechos, which can create massive wildfires with like pyrocumulonimbus clouds. So getting new phenomena like that. And these storm clouds, when they're more massive than before, if you look at most people are familiar with the cumulonimbus storm cloud, very dark cloud. Dark because there's a lot of water droplets and they're large, they absorb light, so the cloud's dark. And these clouds extend all the way up from the surface up to the tropopause, which is a dividing line between the troposphere and the stratosphere. Most things don't penetrate up through that layer, so you get this flattening of the cumulonimbus cloud like an anvil, right? That anvil shape, and that flat area from the anvil is basically the tropopause, where the temperature is stable. It doesn't drop with elevation, it's stable. And then you go into the stratosphere and the temperature is actually increasing. So there's like a barrier, but my point is, if the convective uplift is strong enough in these storms, and that happens more and more often, then you can get the water vapor and convection breaking through the barrier and going into the stratosphere. And this water vapor reacts in many different ways in the stratosphere, but you can generate these polar stratospheric clouds and stratospheric clouds. Often they appear purplish or bluish, Sometimes you can see them from the ground. They show up on radar and from satellites, but we're getting more and more water vapor going up into the stratosphere. The other thing that's important is, of course, when there's volcanoes, it injects ash right up into the stratosphere. And so it's not rained out. These particles are not rained out. So they stay in the stratosphere for 2, 3, 4 years. So when there's a large volcano that is putting ash upright into the stratosphere, it can cause a cooling of the planet for 2 or 3 years. So think of Pinatubo, think of some other major volcanoes, and you can see how the effect is on the temperature. And this leads to the idea that, we're human, we should be smart, we should be able to do something like stratospheric aerosol injection and put up particles to cool the planet. This is solar radiation management type things to allow us time to restore the planet by reducing greenhouse gas levels, by protecting some things that we're losing. So that's a whole other area, but the role of the stratosphere is crucial for climate. So well worth learning a bit more for our viewers about the stratosphere and the various effects that are going on. So we're focusing on ozone, but also, it's very important when water vapor gets up there, you get these clouds and other effects. When aerosols get up there, you get some cooling because they're blocking the incoming solar radiation. So there's lots of different effects that come into play.
Thank you, Paul. And Peter, I know that you're very familiar with the ground level ozone effects on human health. And sometimes those two issues, the ozone layer up in the stratosphere and the ground level ozone, often get confused. Can you provide some insight on that?
Yeah, as I say, they do interact both ways, but ozone depletion does not cause global warming and climate change. So what is called tropospheric ozone, for those of us who are slow to understand these things, it's a better term surface ozone or ground level ozone. It is a greenhouse gas that has some potency, but it lasts a very short period of time in the atmosphere. But because we are producing all of these gases constantly, gases that don't last as long as CO2 are, in a way, no less important of CO2. So ground level ozone is a product of the fossil fuel industry. It's another harmful killing product. There's an interaction between oxides of nitrogen and volatile organic compounds, particularly in urban regions. And that reaction that results in ozone, ground level ozone, and other chemicals is catalyzed by solar warmth. So I've always been more than extremely concerned about ground level ozone because it's very, very toxic to human beings. It's a highly toxic air pollutant, and there's no safe threshold for it. But because we're still burning fossil fuels, we're still getting this ozone problem.
I'll add to Peter's some of his points on ground level ozone, because a lot of it's coming out of the tailpipe of fossil fuel powered cars. The best example of ground level ozone is if you have your toaster starts to spark or your microwave starts to spark, and then suddenly you get this smell, right? This pungent smell. And if you've got electrical sparking, that can break down air molecules, oxygen, into singlet oxygen, which is highly reactive, and each singlet oxygen can go and join with an oxygen molecule, forming the O3. And O3 is very, very unstable, as Peter mentioned. It's also very, very harmful to your health. So even if you have appliances powered by natural gas, by methane, like your stove, some heating systems, water tanks, sometimes, if you get leakages or incomplete combustion of that gas can generate some ozone. It also generates benzene. It also generates CO2. So all of these things can be measured. And I'm reading a book right now, which is relevant. Okay, this book here. I'm going to do a book review on it, but Rob Jackson, there's a section about some of the things that are coming off natural gas appliances within your home. So they've gone to many different people's homes and measured things. And you can get instant rises of PM 2.5 particles, of CO2 levels can go up 4 or 5 times in your kitchen, carry to the bedroom of the house down the hall. Ozone's there, benzene's there, all of these different things, which they've actually measured, and he goes into detail on that in a particular chapter on it. And these are all health impacts on people that people don't realize. You know, electrification of our society is crucial. And then for that, of course, we need the sources of electricity feeding the power grid to be sustainable, to be non-fossil fuel as well. So I just want to make that, you know, connection, because so many things are connected. I mean, we do videos on a specific topic. Some people may argue, well, there goes Beck with rambling off on a tangent, but you know, maybe I am, or maybe I'm just trying to join the dots, you know, and connect, you know, one thing to another thing to another thing. So yeah, ground level ozone is a problem. It also stunts vegetation. It stunts, if ground level ozone is high, and it's not just in an urban environment, like in, you know, with tailpipes. It could be, there's some regions where ground level ozone is very high, especially on elevated, you know, if you're on a mountain meadow or something, you know, you're up hiking there, suddenly you have trouble breathing. It could be out ground level ozone descending high amounts for whatever reason. And if it's there persistently, it can stunt the growth of trees, of grasses, of anything, any living thing is negatively affected by the ground level ozone.
Thank you so much, Paul. Thank you, and thank you as well, Peter, for all your insights on this topic. And we thank you, our audience, for joining us here today. And if you learned something from this video, please consider liking the video. And if you haven't done so already, subscribing. And so we look forward to seeing you again on the next Climate Emergency Forum.